In this video, we're going to look at electrophilic reactions. So the first one that we'll take a look at is electrophilic addition. So alkenes undergo electrophilic addition. And what happens is atoms or ions, which are known as electrophiles, are added across the double bond. So the weaker pi bond is broken. Remember, the sigma bond is stronger. And the atoms in the electrophile will bond with the carbons. Alkenes are more reactive than alkanes because the electrophiles can more easily break the pi bond than a sigma bond. So just to recap what an electrophile is an electron deficient ion or molecule, and it will be attracted to the carbon-carbon double bond. It will accept an electron pair from the nucleophile, so the nucleophile will be the alkene this time. And halogens can act as electrophiles when they're close to an alkene as well. And we'll outline that on the next example. So first we'll look at the reaction with bromine. So when bromine gets close to the alkene, the electrons in the bromide atom that is closest to the double bond will get repelled, and that will cause an induced dipole. The two electrons in the pi bond will covalently bond to the nearest bromine atom. So you can see that happening here with this arrow, which will break the bond between the bromine atoms. So then the bond is breaking. So you end up with a carbocation and the bromide ion, and they will form a covalent bond with themselves as well. So you'll end up with one replacing, and then the second one will come in and combine with the carbocation. So when you're reacting with a halogen molecule, you'll end up with two halogens being substituted or added across the double bond. So you'll have, in this example, 1,2-dibromoethane. Now the same process will occur with hydrogen bromide, but this time, because there's already an electronegativity difference between hydrogen and bromine, hydrogen has the positive dipole, so it will first react and replace the one double bond or the pair of electrons, and then the bromide ion would then come in and bond as well. So we don't have to induce the dipole this time because hydrogen bromide already has one. So we also need to consider what happens. So far we've looked at symmetric alkenes, so they're exactly the same on both ends, but sometimes there's more than one option for placing the halogen. So it could either go on this carbon or this carbon. So we need to follow Markovnikov's rule, which is that the hydrogen needs to be added to the carbon that already has the most hydrogens. So if we look at this example, the top one, they put the bromine on the end carbon, but that was the carbon with the most hydrogens, so we needed to put the hydrogen there. So this one is not the one that we would favor. This is the one we would favor because the hydrogen should go on the one that has the most hydrogens already, so like that, and then the bromine would go on this carbon instead. It's the one with the fewer hydrogens. So we would end up with 2-bromopropane. So if we look at the example of interhalogen halogens, so that's when you have two different halogens bonded to one another. So in this case, iodine and chlorine. So instead of hydrogen bromide. So the one that has the least electronegativity will be the one that will act as the electrophile. So it's going to act in the same way the hydrogen did in hydrogen bromide. So it's going to be added to the end carbon following Markovnikov's rule, and then the chlorine will be added to this one. So you can see that in this example. So let's take a look at benzene. Because benzene has delocalized pi electrons, it's prone to attack from electrophiles. And the reaction progress is seen here. So we see our energy diagram. So there's quite a high activation energy for this reaction. And because of that, that tells us how stable benzene actually is. So it's not an easy reaction. And we can see that it's a substitution reaction that occurs because we maintain that the ring. So in the reaction, the electrophile removes an electron pair and it disrupts the delocalized pi electron system. And it gets restored, however, when the electrophile replaces a hydrogen. So the hydrogen leaves, the electrophile goes in, and we still have maintained our benzene ring. So we can create nitrobenzene from benzene under reflux conditions at 50 degrees Celsius. So if you go higher than that, it's not going to only substitute or add on one of the NO2s. It'll actually start adding multiples, and we don't want that. So we have to do it under reflux at 50 degrees Celsius, and we have to do it in a concentrated solution of sulfuric acid and nitric acid. And there's actually multiple reactions that occur. So the first thing that happens is sulfuric acid donates a proton to nitric acid. So we then end up with this ion. And then that ion loses a water molecule to become NO2 positive, and then the resulting nitronium ion is now free to undergo the substitution with benzene. So it'll take the electron pair from benzene, and then it will replace the hydrogen and then substitute itself on. And then we end up with a hydrogen ion remaining.